So welcome back. Before we talk in the previous class, we talked about how lift is generated in an airfoil. Now let us look deeply about what type of drags are present, drag and lift forces, which we saw previously. Let us take a closer look to it. So consider this as an air friction like friction. This is also dissipative in nature, and hence it affects our speed and fuel economy. And therefore, we must reduce drag at all cost. We must try everything at our disposal to reduce the drag force. So before trying to reduce, let us check how many types of drag forces are there. So broadly, we can classify into two types: one which is independent of lift, and other which is dependent on lift. So this type, which is independent, it does not have any component of lift. So this there is two types of drag which fall under this category. The first one is skin friction drag, other one is pressure drag. If you look at the second category, this is dependent on lift, and this is called induced drag. Why induced drag? Because the drag here is induced by the lift force. As the lift force increases, the induced drag also increases. So let's look at skin friction drag first. This is one of the major causes of drag, and it acts along the interface of solid fluid layer. So this is the solid boundary, this is the solid surface, and this is the air stream moving. So it occurs at the solid fluid layer interface, and hence it depends on both the fluid viscosity, the viscosity of the fluid, and the surface roughness of the surface. So what we see that there is a very important condition that any surface which is moving through a airstream at the particle which is very adjacent to the surface, particle adjacent to the surface remains constant. Okay? This means that the relative velocity between this surface and the air particle adjacent to it is relatively zero velocity. That means this is stick to the surface. This is called as a no slip condition. The air particle surround just adjacent to the surface is at rest, and as we have seen that farther away, the airstream is not disturbed by this surface, and that undisturbed region of air, this is called as a free stream velocity. The velocity of the undisturbed region, this is called free stream velocity. This remains constant throughout. So we see that here the velocity, the particle velocity is zero. Here the particle velocity is free stream velocity. So in this region only, the velocity has to increase from zero to free stream velocity, and the region where this flow slowly gradually increases to free stream velocity, this region is called as a boundary layer. And if you remember, at the very first lecture I told you that this boundary layer is a region where the viscous forces are prominent. There is a region where viscous forces are prominent, and because of this viscous forces which are present here, this creates a skin friction drag. There is a relative tendency to move one layer above the other, and that creates a drag which is called as a skin friction drag for this surface. Now this is for a laminar flow where there is no mixing and the fluid flow in an ordered way. What happens is the velocity increases, the velocity of the free stream air increases, or there are roughness, or the surface is very long. So in that case, the laminar flow get converted to turbulent flow, and in turbulent flow what happens is that there is mixing of air. So what happens is that the high pressure, the high velocity airstream get mixes in the lower region also. So that means that the no slip condition is still valid. This velocity is zero, but the transition from this zero velocity to the free stream velocity is very rapid because of this mixing. So this thing is very rapid, and what happens because of that, there is the shear forces which are involved in this viscous region is higher, and that creates larger skin friction drag. So skin friction drag increases in case of turbulent flow. This GIF will explain this thing much better. If we see that when the laminar flow gets converted to turbulent flow, see how this boundary layer changes. This is the boundary layer initially. After turbulence, this boundary layer changes significantly, and the skin friction drag also increases. See, it increases rapidly in the turbulent region. See, there is mixing of. So in case of skin friction drag, we want to reduce turbulent flow as far as possible. Let's look at the second type of drag. This is called as a pressure drag. This is also called as a form drag or the profile drag. This is because the form or the profile or the shape of the object creates a region of high pressure region here and a low pressure region at the back side. So that creates a drag force. Why is that? Because it obstructs the airflow here. So this creates a high pressure region, and at the back side very little air particle are there, so that creates a low pressure region. So high pressure region here, low pressure region here, the force acts in the backward direction and that tries to stop it. So that is also regarded as a drag force. So here the shape and the angle of attack are very important considerations. So let us see why this thing happens. This is called as the wake of the object. The object is moving past this region, and there is a low pressure region created. This is called as the wake of the region. So let's see why this thing is created. First, put your attention to this side of the object. If we take an imaginary line here, this is the surface of the ball which is shown here. This is the surface of the ball and these are the streamlines. See, the streamlines are spaced apart here and constricted here. These are spaced apart here and constricted here. So what happens is that the area of the streamline, the area enclosed, if you consider this to be a cylinder, so the area enclosed is getting reduced. And if you remember your continuity equation, what happens in a continuity equation? As the area decreases, the velocity increases. So area is decreasing, velocity is increasing. And in the Bernoulli's equation, as you have seen, that as velocity increases, pressure decreases. So what happens is that this is a high pressure region. This velocity decreases here and pressure increases here. Sorry, velocity increases. This thing, velocity increases from here to here, and as velocity increases, pressure decreases. So this is a high pressure region, this is a low pressure region, and the flow takes place from high pressure to low pressure. This is the favorable condition. The flow always takes place from higher pressure, wants to take place in from higher pressure to low pressure. This. So that is what happening here. If we take that, this is the positive x. As we move along the positive x, the pressure decreases. This is called as the favorable pressure gradient. Mathematically, it can be written as this. The dou p upon dou x is less than negative. This is called as a favorable pressure gradient. So as the flow is taken in the high pressure to low pressure region, favorable pressure gradient, no flow reversal and flow separation takes place. This is the favorable flow direction. So no flow separation occurs here. Now let us put our attention to this side. What happens here? So this is the exact opposite of what we have seen here in previous condition. So here is our reference line, initial line. This is the surface of the ball. Here we can see that the area is increasing gradually. Area is increasing from continuity equation. As area increases, velocity decreases, and as the velocity is decreasing, moving around positive x, the velocity is decreasing, and hence the pressure is increasing. So here this is low pressure region and this is high pressure region. So the flow is taking place from low pressure region to high pressure region. This is not the uh, this is not the gradual flow. This is not what the fluid wants. It does not in practice it does not wants to flow from low pressure region to high pressure region. This is called adverse pressure gradient, and mathematically this is the condition that dou p upon dou x is greater than 0. So what happens here is that you might ask that how the flow is taking place from low pressure region to high pressure region. It should always happen from high pressure to low pressure. But here you must remember one thing that I have told you in the Bernoulli's equation, that pressure is not the only thing which we need to consider. The dynamic pressure or the pressure created due to the flow is also there. This is the dynamic pressure and this is because of the flow of the fluid. So as if the velocity is high, even if this part is negative and this part is substantially positive, the total sum will come out to be positive and the flow will take place without any flow reversal. So remember that, but this does not happen always, and uh, this could not compensate for this adverse pressure gradient, and the flow which was taking place in this direction would starts to move in the backward direction. That creates a swirl here. So this becomes the velocity profile which we have discussed earlier also. The velocity profile changes here. the no slip condition still stays true. This particle is 0, but adjacent to it the velocity is in the negative direction, negative x direction. Then it becomes again 0 here. After that it again increases in the positive x. So what happens that the flow which was taking place like this, here this could not take place as they were the flow is reversing its direction. So the flow now takes place in this direction, this one, it moves in this direction. So this is the surface, this is the surface of the ball, and the flow is taking place around this direction, and this region there is a circulatory flow. So what happens, this is the surface and this is the flow. So as you see that flow is not in contact with the surface anymore, it has detached from the surface, and this is called as a flow separation. It's called as a flow separation region. So anywhere you see there is a diffusive region, diffusive region, you have to be very careful that the flow does not separate. Flow should not separate, the angle should be very less. This flow separation should not occur, otherwise there is very high pressure drag. So this is a very good example of how why this golf balls are dimpled. If you see that this is a very smooth ball. So what happens with the smooth ball is that the turbulence is low, the laminar flow takes place here. As we have seen, smooth region creates laminar flow. So this is good for the skin friction drag which you have seen. The skin friction drag is less in this case, but see here the flow is separating here only, and this creates the wake and the recirculatory flow which I was talking about. So here only the flow gets detached from the surface, where in this case, since this dimples or small dips are created around the ball, what happens is that no doubt the pressure drag, sorry, the skin friction drag increases because turbulence get induced here. But because of this turbulence there is mixing of flow, so this flow gets mixed around. As you remember here, it flows mixed around, and high velocity air particle comes very close to the surface. So that thing makes the flow separation bit late. This velocity terms increases here, and because this velocity terms increases, the total sum becomes much positive, and the flow which was detaching very early on, it was detaching here, so that detachment is delayed. It is now detaching at somewhere this region. It was initially detaching here only. So that's why golf ball are designed this shape. So as you see that turbulence is not good for skin friction, but it is good for pressure drag. So you need to take this two into consideration and make your design such that the sum of these two drags becomes minimum. Alright. Okay, now let's talk about the other type of drag, which is induced drag. Now, this type of drag is a direct result of the pressure differential which created the lift force, and hence it depends on the lift force created. That is why it's called induced drag. This was induced because of the lifting component. So as you remember, this is our wing. This is our wing, and the wing, what it does is that this creates a region of high pressure at the bottom and low pressure at the top. In case of aircraft, in case of cars, this thing is reversed, but still there is a difference in pressure. The pressure is differentiated. Here it is high pressure, here it is low pressure. So the air particles does not wants to remain segregated like this. It wants to reach an equilibrium state, or they want to neutralize. So what they does is that they can't move right here. This creates the lift force. This pressure difference creates the lift force, and they want to neutralize it. So what they do is that they curl around the wing. So they curl around the high pressure air particles here would curl around the wing and move in this direction. This creates high turbulence and high vibrations. Okay, this is also not very favorable for us. See in this the aircraft wing is producing this vortices. This vortices because of the induced drag. The high pressure region here would curl around to get to the low pressure and neutralize. So that creates this eddies. So what engineers have done to reduce this is that at the wing tip they creates this kind of edge or this kind of bend. This bend keeps the high pressure and low pressure region segregated. You might seen this kind of thing at the rear wing of Formula 1 cars. So this also keeps the low pressure and high pressure region separated. See, this is the winglet. This is called winglet of an aircraft. This separates the high pressure and low pressure region distinctly. This is from a race car. All right. So let's stop it here. We will talk next in the upcoming series.